Thank you all for coming to our latest NASA at Google Talk. I'm very, very pleased to welcome Guillaume Bratt, who is going to talk today about reducing the cost of impact of V&V for flight critical systems, as you can see.
It's a mouthful.
And it is. So is your bio. So Guillaume comes from us from UT Austin, where he has his PhD. He is the area lead for robust software engineering in the Intelligent Systems Division. He's also a technical lead for autonomous system assurance in the Safe and Autonomous Systems Operation Project and for air traffic and vehicle software and system assurance research. Thanks so much. Here's Guillaume.
All right, thank you. Thanks for coming. So, I wasn't expecting that many people, especially for a talk about V&V. Usually doesn't draw a crowd. So, as Mary said, I'm leading a team at NASA Ames that's about between 30 and 40 researchers and developers. We have about 25 researchers that do mostly research on formal methods and their application to software verification, and about between 10 to 15 engineers, depending on the time, that are really focusing on developing what we call flight critical systems. So those could be control systems or spacecrafts, mostly on the space side. The research I'll talk about is mostly done on aeronautics, so it's not so much applied anymore on the space side. We'll try to infuse it on the space side, but it's really targeting at civil aviation. Okay? Basically, about 6 years ago, NASA was told by OMB, the White House, to start addressing the cost, what they see as the cost, the high cost of V&V in the civil aviation. So basically, that's the manufacturers like Boeing, Embraer, and all those guys, and the OEMs that are working as subcontractors to those, we're complaining that the V&V for software is becoming more and more of a cost for them and is basically hitting their lunch. So they wanted somebody to address it, and basically that mandate was passed on to us at NASA to try to address it. So we set up it was backed up by several surveys that have been done by the DoD, by external civil agencies. You can see at the top, there is the decadal survey for civil aero, and it's pointing out to the fact that you need new methods and models for assuring safety. So when we talk about V&V, safety is the biggest target for us at NASA. Okay? Then there was the integrated plan for the implementation of NextGen. NextGen stands for the next generation of air traffic systems. Okay? And they also pointed out that there was a lack in V&V, a lack of methods to really address those type of systems. The Air Force did also their study, and they actually identified the same need. There's not enough V&V techniques that are available to really verify the type of systems they're building. So we actually, since then, we've been kind of in lockstep with them. The research we are doing is feeding into their program. Okay? So as I mentioned a bit earlier, so that was passed on to us by OMB, the White House, Congress, all those big, governmental agencies. But really what's happening is behind the scenes, you have the CEOs of companies like Boeing, Rockwell, Honeywell, going to really say, going to our chief at RMD and says, it really is costing us way too much money to do V&V. And especially V&V for software, and software is becoming a larger part of the cost of developing a plane. So what you're seeing here, a pie chart that tells you pretty much how much it costs to develop a new plane. That's coming from a major manufacturer, the biggest manufacturer of airplanes in this country, which I won't name, but you can guess. And if you see, software and software VNV is taking like almost 70% of the cost now. The part about the design of the plane and those kind of things, it's 30% these days. That explains to you, if you want to quit Google, you can get a job in the aviation industry. They are hiring a lot of software engineers these days. Okay, you just have Java is not the language that they will use, but. So really what we've been asked to address is that cost, especially for what we call the flight critical systems. So that includes the flight management system, the flight control system, the software that's controlling engines, and all the system integration on the plane, right? Because that part, the system integration, is important to consider because before, Boeing, for example, was building everything end to end. Nowadays, they rely on a lot of subcontractors, and they're integrating a lot of cuts in their systems. So this is a new business for them, and they don't know quite how to deal with it in terms of VNV. So what drives the cost of VNV is mostly driven by this certification standard that software has to go through for airplane, which is called DO-178. We had the third iteration of DO-178. Now it's DO-178C. And DO-178B was all about doing the VNV through testing. DO-178C now allows you to take advantage of what's called formal methods and model-based development to actually do some of the VNV upfront. Okay. So in 2010, we started to build a program that was supposed to address it. There's the software aspect, but there are many aspects, especially when you want to take into account also what's happening in terms of computer systems in the air traffic management part of this equation. So we had 4 foundational research elements. I'm going to start with the top left, and this one is called argument-based safety assurance. So in that one, we're looking at different ways of doing certification than DO-178. If you're talking about applying formal methods, it's really formal methods. When they're applied, they're retiring a specific risks in your software. DO-178 is all about building quality in your software rather than addressing a specific risk. Okay, so we wanted to change that, and it's a move that has been done in Europe, or at least parts of Europe. In the UK, they're using safety cases, which are really argument-based. They're addressing specific risks for almost all the defense contracts nowadays. Okay, it's not used so much in the US, except for when you want to introduce what they call an experimental plane. And this is where you guys might be a bit interested, because a drone, for example, a UAV, is an experimental plane. There is no really a good guideline on how you go about doing the assurance of drones these days. So right now, the FAA is requiring a safety case to be able to operate any UAVs. Okay. Now, the other 4 elements, I'll talk about those 2 together. All those planes are operating in what we call the NAS, the National Airspace for the US. So think of it as the whole air traffic system within the US. When we got that mandate, it was said that the traffic would be basically multiplied by 3, by a factor of 3, within 5 years. They since then backed down from that, but they're still forecasting a huge increase in traffic, which means more density, which means the safety margins are going to be reduced a lot in air traffic. So they wanted us to also look at that aspect of civil aviation. And if you look at the NAS and the way it's operating, it's basically a huge distributed system. It's a huge distributed system where you have automation, You have computers interacting with all kinds of humans. That includes controllers, pilots, the airline management operation center. So it's really a mix of computer systems and humans interacting with all the confusion that can arise from that mix. And we decided that the human element was so important that we pulled it in a separate element that we call authority and autonomy. So the autonomy part is about increasing automation for those air traffic systems. And the authority is, as we introduce more and more automation, more and more autonomy, we're transforming the role of the human in that system. And the fundamental question in the end is, who has the authority to make the decision? Do we leave it to the machine, or do we still have a human that pushes a button and says, okay, go. The machine was right, this is what we should be doing, okay? And on the distributed system part, we kept focusing mostly on the complexity that's increasing within aircrafts. Aircraft have gone through a change. They used to use what we call a federated architecture, meaning you had one box per function for the software, which means that everything was well separated. And there was a move to what's called now an IMA architecture, which stands for Integrated Modular Avionics, which actually is a way of putting everything on the same boxes. But now the FAA requires you to show that those functions are residing on the same physical boxes are separated from each other, either in terms of the memory they access, or in terms of time, they're running at different times and they cannot interfere with each other. And that's a lot trickier in terms of verification, this type of architecture. So they also have a tendency to put a lot more things on the plane. It used to be that most of the decisions were done on the ground, and then you upload the sequence of actions to the pilot, you tell them what to do. Nowadays, there's a lot of functions are migrating from ground to airborne, and that means the software on board the airplane is a lot more complicated. That goes beyond that. If you look at the Boeing 787, it has something that made everybody nervous, because they went from having 2 or 3 physical networks that were completely physically separated on the plane to one physical network where the separation between the functions are controlling the airplane and the functions are controlling your entertainment systems are using the same bus, but they're basically walled off by virtual mechanisms. So that made the FAA extremely nervous, because they think you can hack and then cross over. And there is a famous guy that keeps saying that he's hacked into the control system for several United flights, and kind of, frankly, it's a myth. But that makes the FAA nervous, and they want better verification techniques to address those things, okay? So that's the setup. And the part I'm going to concentrate on is the software-intensive part. So really, what are we doing about the software-intensive system? And mostly the part that's about airborne systems, meaning all the software that's on board the aircraft, okay? And hopefully by the end, I'll make the transition to the new things we're supposed to address, which is autonomy, complex system, okay? So most people say VNV costs too much money. Actually, that's what the manufacturers are telling our management. It's not really VNV, let's be clear. It's not VNV per se, or doing the VNV that's costing you a lot of money. That's where you're doing it. So if you look at the V diagrams and the phases of development that are used in the aviation industry, goes from requirements, very careful requirement developments, then design, then coding, then you move on to testing, unit testing, integration testing, acceptance testing, finally you deploy. Very long cycles. And all the VNV in traditional aviation is done here on the right side, on the testing part. So the problem with this is that not only it costs a little more to do it there, but all the faults I found here when actually the faults are being introduced way before. So when you do this, that means that every time you want to fix a bug that you found, you have to go back to some of those earlier phases. If you go back only to coding, that doesn't cost you that much. If you go back to design or requirements, then that costs you a lot of money. And that's usually where the cost is coming from in the additional cost that's coming from in VNV. So the whole program was geared towards pushing the VNV to the left side of the V, make it available as soon as possible. And I want to be careful here. It doesn't mean that we get rid of testing. It means that what we want is fly through testing and not find any bugs, okay? There shouldn't be anything left when we run the tests so that we don't have to go back that design loop, over that design loop, okay? To give you, to really hammer the point, NTSB is the board in the US that's investigating all the incidents and accidents in aviation, and more than that in transportation actually, but in aviation in particular. They've traced that 90% of the accidents are due to requirement problems. So really, the pot of gold is right here. We really need to be able to address this, okay? So our whole program was to try to push the VNV to the left, okay? What we started to do is by giving them better techniques in terms of testing. Then we moved down to giving them techniques they could use during coding, and that's mostly static analysis type of things. And then to design, and it's like, for you guys are familiar with formal methods, it's model checking type of technology. And then what can you do at requirements? I'll save this, I don't have a slide on this, but if I skip it, Mary, flag me, because I need to talk about it a little bit. So it can go all the way to using theorem proving to formalize and prove formally that an algorithm is correct. So that's what I just mentioned, and those are the tools that we have developed at Ames. You got to know that most of the 50% of the work in VNV and under that program is done here at Ames, next door to you guys. I can see your buildings. I'm kind of surprised I'm not in the building that I see directly from my office, but and the other half is done at NASA Langley in Virginia, in Southern Virginia. But we are, I would say, a little better than Langley at developing tools that are practical for use in coding, model checking, and requirements. Okay. So let me start with the first one. What did we do to improve testing? Most of the testing is very well done. It's really very well done. What might kill us and what we see seeping through is really the outliers, the events that are extremely rare and that might still cost you tons of money, okay? So we went after this, and we went after this using statistical learning. The way it works is basically you use your typical test cases, you run them, and then you do a statistical analysis on your output to see if you have outliers in your data. So an outlier is not necessarily something bad, but it could be indicative of a bug, okay? So there's a human making that determination. Is that an outlier that's indicative of a safety issue or not? If it is a safety issue, what we want to do is try to learn all the other, because it's not just one single data point, it's actually a region that's unsafe. So we want to learn what inputs can drive to that unsafe region. We want to identify that unsafe region and find the inputs that's going to drive there. What that gives you is that after that, a way of of telling I shouldn't operate my plane at that type of in that type of situation. Avoid this because a problem might show up. So if you don't believe that's a problem, or it's a way of solving problems in aviation, Airbus had an incident at one point where basically there were data that was accumulating and creating overflow errors, okay? And they found that they couldn't find it for the longest time because it was happening only after 24 hours of flight, basically. So for the longest time, they couldn't find this, and then it was showing up in some cases. So they decided that to fix this, rather than redesigning the software, revalidating it, they decided the fix is easy. Now, before we reach the 24-hour period, we reboot the system completely, clean, right? Easy fix. It's still in the system, but it won't show up, right? But that was one that was extremely rare to find. It was in very particular conditions. So this technique is trying to go after this kind of stuff. Every time you identify the problem, then you use statistical learning to refine your test cases and try to drive to this region that could be unsafe. Okay. It was done on single input, and we moved it to time series because when you try to apply it to air traffic control, then you don't reason about single input, you reason about trajectories. So you need a time series, something that allows you to reason about time series in inputs and outputs. Okay? There is a second use of this. Very often when you use formal methods and you apply it to the verification of software, it's too complex. And sometimes you want to be able to drive to a specific region of behaviors that you want to explore fully. You can use this type of technique to actually find the point much quicker, the point that will allow you to just focus on one single region. Okay? So you will use this first, and then once you have identified the region, you do an exhaustive search using some kind of formal methods. All right, so that was the testing. Like I said, after that, we tried to give them tools that they could use at the code level. So I'm sure you guys are aware, there's plenty of static analyzer, commercial static analyzers that are out there these days. To name a few tools, there is Grammatech, there is Coverity. There's been some consolidation. The names might have changed 3 years ago, but those are the kind of tools that are out there. Here's the problem with those tools. They're extremely fast. They can deal with really big software. We're talking million lines of code very quickly. But all they're giving you are warnings. Because to be fast, they have to cut corner and they're unsound. They cannot tell you for sure that you have a bug or that you don't have a bug in part of your software. Okay? So what you end up doing when you're using this is that you get lots of warnings, for one thing, and then you have to review every one of those to see if it's really a bug that you should be addressing or not. So that means a lot of manual work. So what we went after was the type of static analyzer that could tell you exactly for sure that you have a bug. That's what we call, as opposed to warnings or of warnings that can turn into false positives. Okay? And the added benefit is this type of tool can also tell you when they're sure that you have no bugs on that instruction. So it doesn't tell you that for every type of bug that you can have. It goes for what's called runtime errors. So the typical ones are buffer overflow, uninitialized variables and initialized pointers, division by zero. It can catch some floating point errors in terms of rounding off and those kind of things. Okay? So we created a tool, and I'm surprised I thought Arnaud would show up, but because the guy who helped me create this tool is actually working here now, doing that for you guys. But we were doing it for C and C++ because those are the languages used in flight critical systems. Okay, And that we've showed in all the applications that we've done of those tools that we could go to what we call a precision rate of 98 to 99%, meaning that we had only 1 or 2% of the checks that we were making where we couldn't tell you for sure that you had a bug, or we couldn't tell you for sure that it was safe in terms with respect to the classes of errors that we were tracking. Okay? Which is much higher than any of the commercial tools. One that's coming close to doing this is a tool that used to be called Polyspace Verifier, which is now called, has been bought by the MathWork, I can't remember the name, but it's folded into the MathWork suite of tools. And typically when I used it, for example, on controlled systems that are close to the avionics, but they were on the space side, I had between 20 to 50% of warnings. So imagine on 1 million lines of code, you almost have a check per line. That gives you 200 to 500,000 checks that you have to go through and say, is it really a bug or is it not a bug? It was the main reason for that, why for the longest time people were trying out static analysis tools and were throwing them away, because it really wasn't giving enough useful information. So what we wanted to show, we didn't set out to build a tool that we can sell and say we're better than anybody else. But the goal is to show the industry that are building this type of tools that you can do it. It's possible. Here are the techniques that we're using. Use that in your tool, and then you can do better. Okay? If you guys are interested in using it, it's been open source since 2014. We still work on it, trying to refine it. If you download it and use it and find problems, please send us feedback, because we're relying on the external community to make the tool better. All right, so that was at the code level. Now let's move to the design phase. And there the goal is to try to enable model checking on the models that are used at design time. Okay? We could have gone the way of picking a formal language to represent models and use the model checkers that are built for this. The problem is that most of those formal languages are not used in industry. And our mandate is really to have an impact on industry. It turns out industry for flight control systems and for engine control systems, at least, are using mostly something called Simulink, or SCADE. SCADE is a little bit more popular with engine control. Simulink is more popular with the flight control systems. Okay? So we decided to provide something that could go from those languages that could apply model checking on those languages. So when I say model checking, that means I'm writing safety properties about my system that should hold on my system. That could be the landing gear should not be deployed while I'm in flight, for example. That's a typical one, okay? And then it checks that property, if that property holds on the models or not. So basically you get something like this. You get either a true, yes, it's true if you go with this design, or it's false, and here is why it's false and it's gonna be violated. It's giving you a trace to show how that property would be violated, okay? So we try to enable that from Simulink and SCADE. But obviously we don't want to try to address every language that is used out there, every different language. So we actually hooked up a bunch of model checkers to our own internal representation that's using the Lustre language. So it turned out that makes it easy because, for example, SCADE, the underlying foundation for SCADE is Lustre. Lustre is a data flow language that was developed in Europe for embedded systems, okay? And it turns out that Simulink can also be mapped to that data flow language fairly easily. So what we have is that a bunch of translators that go from Simulink to Lustre, from Simulink or SCADE to Lustre, and then we apply all those types of model checker on it. And this part is extendable. You can add your own. All you have to do is be able to map the representation to our intermediate representation. For example, Boeing is asking us to add new SMV, which is one of the fastest and most efficient model checker out there, to this list. Okay? So we didn't want to stay here because the typical one when you use Simulink is you develop your models in Simulink and then you auto-code into C or C++. Okay? So what we wanted to provide also is a way to doing that at the C, C++ level that was generated. So we have another tool called Seahorn on the bottom right there that actually can do this. Think of it as a sort of static analyzer that can check on C assertions. And those assertions are representing the properties that you verified on the model. So why do we do this? Most people that are looking at it is like, you already verified on design level, why are you doing it at the code level? Because the FAA doesn't trust anything. They require you to check it at the design level, and they're going to want to know that you've done it on the code. And if we were listening to them, they would require us to do it on the executables. But there's way too many targets for us to chase. Okay? So again, this one is available open source. It's been developed partly at NASA, partly at CMU under what's called an NRA. Okay? And we're redoing a version of it that would be only in NASA to make sure that we have a very clean license on it. Same thing, it'll be released open source. And what we want to do is make sure that we have clean APIs so that anybody that wants to add to it can add to it. Okay? And one of the main reasons we're doing this is because we have on this work, we have partners in France at Onera who are working on this type of system. Okay? Well, before going to safety cases, I'm going to talk a little bit about requirements because the next step really should be analysis of the requirements. Okay? So here's the analysis we've done when we tried to see what we should be doing at that level. There are plenty of formal languages that have been created in the last 20 years to formalize requirement and to do analysis on requirement. Nobody, absolutely nobody in aviation are using it. Absolutely nobody. Because they don't like the language, because it's too mathematical, because they have to learn something new. The way it's done in industry is still, I'm writing natural English sentences to describe my requirements, and I put that in the best tool that's available, that's called DOORS, which is a glorified spreadsheet. That's it. There is no formalization behind it. Okay. So the question is, do we go and pick this in one of those languages and try to convince industry to use those? Or do we do something that allows them to go from natural English to formal requirements? And that's what we're trying to do. We try to provide the part that goes from natural English to requirements. There are a number of ways that have been investigated. One of them that's popular and that's pushed at the Air Force, with our partners at the Air Force, which is using English patterns. So you're writing almost English, but you're using only some patterns of English that can be very easily translated into some kind of formal language. Okay? It works up to a point. Really, when we tried to use it, there were like plenty of requirements we couldn't formalize that way. Okay. On the other hand, you guys can give us hope with all the advances in natural language processing. We're like, well, maybe we can deal with it. Not being an expert, I asked around, and they told me, no, you're dreaming. We're not there yet. So we had a kind of you can tell me different. If you can tell me different, I'll be happy to take your inputs. But we went for an intermediate way, where basically we feel that first, to write requirements that will be formalizable, you have to make sure that those requirements are not ambiguous. So you need an interaction and a dialogue between the tools that's going to formalize, analyze, and the people are actually writing the requirements. And that's what we're working on. And we're using some kind of a pattern language, domain-specific pattern language to do this. So what I'm describing is the dream. It's what we're working on for the next 2 or 3 years. We're at the very beginning of this. I don't know when it's going to be available. Okay? But I've been told that you guys are not writing so many requirements, so it might not be useful to you. All right. So now you know what techniques we're shooting for at each phases of the life cycle. Okay. I said at the beginning, DO-178 is a process that builds quality and safety in your programs, but really it doesn't demonstrate that you're addressing a specific risk. And that's what we want to do. So we're advocating the use of safety case where you can have really, you're able to specify your risk explicitly and provide evidences that you've retired those risks, okay? So the reason they went with DO-178 is that it's mostly enforced by a set of standards, you know. I provide traceability throughout, from requirements to testing. I do quality reviews, those kind of things, and then you get a check mark. Nobody is really checking what you've done. If you follow the process, you're done. You're good, right? In a safety case, now, if I really list all my risks and I'm gathering evidences to retire those risks, it can be huge, okay? Now, I cannot have a guy at the FAA that just check box and says, well, you followed this process, okay, you're good. I have to have a guy that actually goes through the safety case and make sure that everything has been addressed properly, right? So building one, inspecting one so that you get your certification at the end are the biggest obstacles to using this type of technology. So that's why our guys set up to actually try to work on this and build a tool that allows you to visualize, to create safety cases and visualize them and inspect them easily. It does some checking for you, but you can guide it and the human can use it to go very efficiently through it, okay? For example, just to give you a flavor, if you manage to formalize your requirement, then they can build the skeleton of a safety case automatically from your safety requirements, okay? It's not complete, but it gives you the big, like 60, let's say 60, 70% of it, okay? Ultimately, all the results of those tools that I've talked about before, the results produced by those tools should feed into that safety case. So that safety case is really the nexus point where everything is integrating, okay? And why I'm going through this, even though the FAA is not using this at the moment, is because when I talk about autonomy, there's going to be a central piece, okay? So let me step back, and what I talked about was mostly about addressing this bottom one, okay? Addressing the cost of VNV in flight critical systems. And then helping the FAA have the right processes and the right training for their people so that they can actually accept what's coming out of those tools. Because DO-178C is not developed by the FAA, it's developed by a consortium under an agency called RTCA, which has people from the FAA, people from aviation, and people from governmental agencies, other governmental agencies. And all those guys are coming to a consensus, writing a document, and then the FAA says, yes, we adopt this as the new standard or not, okay? But that doesn't mean their certifiers actually know what to do with that new document. So a huge part of what our colleagues at Langley are doing is to try to help the FAA build the training materials and educate their certifiers so that they can actually accept what's coming out of those tools. The next thing is, like I said, we were asked to look at air traffic management systems. So I don't know if you guys have ever seen an embedded system for an airplane. and a system for air traffic management. From a software engineering point of view, those are completely different beasts. So, for example, the use of pointers and those kind of things in an embedded system is all very restricted. Anything dynamic is extremely restricted in an embedded system. Air traffic control, everything goes. So if you think just of static analysis, then suddenly what you have that's efficient for embedded system might not be efficient for air traffic systems. So that's going to require us to actually do some adjustments in the tools that we have. And if you're talking about using a model-based approach to building air traffic systems, it's not going to be with Simulink, it's not going to be with SCADE, it's going to be most probably with SysML or at the most, okay? So that's or it may be AADL, but that means that you have to build translators to our Lust language so that we can actually do the analysis of it, okay? And at the very top is what they want us to shoot for eventually, is addressing autonomy. So one thing when you're talking to aero people at NASA about autonomy, it can mean anything from automation to actually autonomy, okay? It is not necessarily that you're using AI in the system. It could be that you're automating a function. So we have to address anything in between those, okay? One point before I go to autonomy. This is not in pie-in-the-sky research. The days where we can play with the model checker and show it on a small system and say, victory, it worked, it's gone. Now we have a mandate that we have to infuse those in industry, those tools, and actually demonstrate that we impacting the cost of VNV in the right way. Okay, so that's why we're working with Boeing, GE, Rockwell Collins, Honeywell, and all of those. Okay. And if you guys have any systems, we can work with you. So that gives you a sense of what was accomplished in terms of tools. I've talked about a few. Things that I haven't mentioned is that when you're starting to talk about complex systems, then model checker is going to explode unless you use some kind of compositional reasoning behind it, okay? And then at the top, it shows you that industry is starting to actually implement those tools, pick up those tools, build on them, and use them on real projects, okay? Now, like I said, we have to address autonomy. Why? Because NASA, in its infinite wisdom, at least the ARMD part, decided we should have 6 strategic thrusts that we need to address. And if you look at the bottom, assured autonomy for aviation transformation is a big one, okay? The other ones, and you might have had a talk by Kai Goebel before, is what's called real-time system-wide safety assurance, which is more about using data analytics real-time on data to try to prevent or predict possible accidents, okay? So that means we have to adapt what we do in VNV. Our charter right now is the flight critical systems, but this is going to ramp down. At one point, NASA is going to say, you're done with this. You created the tools. You went as far as you could in infusion. Move on to complex systems and autonomous systems. And we have to start planning this. So, like I said, the guys are working on safety cases and their tools. We're going to build on them. They've already been using them and building the safety case to get what's called COAs, which are the certificates you need to be able to operate and fly the drones for any kind of operations. And then we built on another work that we've done for the FAA, which is kind of on the side, which is trying to do VNV for ACAS-X. That's an interesting one for us for a very specific reason, is because it's a very new way of building software for aviation. It hasn't been used before. what's happening, ACAS-X is the next generation for collision avoidance. So right now, the ones that all the aircraft are using is called TCAS. And if you look at the way TCAS look inside, it's just a bunch of if then else rules. If this happened, then you do this. If this happened, you do this. Okay? The reasoning is explicit in it, but it's a monstrous software. Okay? And they're never quite sure they haven't missed a case. So in the next generation, they want to do it completely differently. They basically build a probabilistic model of all the collisions that happen, or the all possible collisions that happen given the historical data that they had. And then they do optimization on it for some specific parameters, and the typical one is called NMAC, which is minimizing the number of possible collision, basically. Mid-air, near mid-air collision is what it stands for exactly. Okay? So they solve this, and that gives you a big table, and they put that in a big table where if you have the state of your aircraft and the state of the aircraft that might be in collision with you, you feed that to the table and pops out an advisory. And that's what's going to be on board, pretty much. So what you have is a very simple software, because really what it does is just reading off a table. That's it, right? But all the intelligence, all the rationale behind the advisory is actually done in the model and in the optimization that was done to go from the model to the table. Okay? So in terms of VNV, that's completely different. You can still apply testing. That still works, right? But the space for testing is extremely huge when you're talking about collision systems. So if you want to do anything smart or anything that's like a bit clever, then you have to do the reasoning on the model and how the transformation from the model to the table is done. Okay? And if you look at it with the past experience of what was done at NASA in autonomy, it's new for aero, but on the space side, it's been worked on for the past 15, 20 years. Terry gave a talk? No? No? He should. You should ask him with the history of how it's done. Well, it goes way back. Julian could testify to this. So if you look at what was and how that was done, the autonomy, there is almost always some kind of a model-based execution that's at play there. It could be the model could be a physics model of the spacecraft so that you can do health monitoring. You compare the data to that physics model. When you have a mismatch, then you get an advisory. Or it could be using a planning and scheduling system, or it could be new techniques like machine learning or reinforcement learning type of techniques. Then your model is more in your reward or utility functions, right? But the bottom line is that it's not in the code anymore. So that's why this type of work was a good stepping stone for us to think of what can be used in autonomy these days. So when you talk about autonomy, most people tell you, well, but what do I do about unknown unknowns, you know? And that's very true. I mean, there is no way with the type of autonomy that's being discussed now that we'll be able to predict all the risks at design time. The environment is changing completely, can throw you off completely. There is no way you're going to be able to predict. So you're going to still have to do some at design time, some VNV, like the classical we've seen, but you're going to have to be able to do something at execution time. So most people are thinking, when we think about this, about runtime assurance, what's called runtime assurance, which is runtime monitoring, and being able to basically monitor a system and do something in real time. Where it doesn't work with the FAA is that you still have to kind of certify that you're doing the right thing. So you can certify the runtime monitoring system, but proving that you have enough monitors to catch all the possible problems is not possible. So somehow we'll have to come up with a system, especially if we're talking about drones all over the place delivering packages and flying in urban environments. We'll have to have a sort of a verification loop in real time that can provide you some assurance in it. So to do this quickly and to have a really tight loop, I can tell you when I tell that story to the traditional aviation, they look at me like, you're nuts. But I'm hoping you guys will be more receptive. If you're telling me you're nuts, then I'm nuts. But to get really a tight loop there that can do some kind of certification, that means behind it, you have to be able to reason about risks, even though you haven't identified those risks. So this is where we look at the safety case as something. Right now, safety case is done at design time. I check it, I get my certification, it goes into a drawer, nobody looks at it anymore, right? Our thesis is you keep this, and this is a live document throughout the life of the system, all the way until it's retired, okay? And you use this to actually reason about risks. You add risks to it, but that means that you're able to reason and identify risk about your domain, your application domain. So this is what, I'm not expecting you guys to go through that whole picture, but this is pretty much what this is saying in here, okay? And like I said, the traditional industry is looking at us, I think, you guys are nuts, you'll never get there. But that's what we're gonna probably shoot for in the next 5 years, okay? And this is the research foundations that we'll do, a lot of formal domain theory, semantics-driven safety analysis, big one. Bidirectional transformations between the arguments and the artifact, because the FAA always wants traceability between everything, okay? Probabilistic analysis and systems to actually help provide information. And this is it. This is all I have today. I'll be happy to entertain questions. If it dives deep into a technology that I don't know enough, I'll provide you the information of the guilty party. Okay?
Guillaume, how much of the problem of verification, especially at the requirements level, is modeling the system and how much is modeling the environment?
Truthfully, in terms of the requirements, you don't have that much about the environment. It's mostly about the system. So yes, that means that there is a part that's missing in there. And that part, especially if I'm talking about addressing all the risk, the possible risk, it has to come from your safety case. Because the beauty of the safety case, so I should say that when I talk about certification at the FAA, and when you do DO 178, it gives you what's called the airworthiness certificate. Okay? It's not on the software, it's on the system that's using the software, but you get airworthiness. That means you're worthy to go in the air. That doesn't mean that gives you the right to operate. There is a second stage that looks at your operational part and how and what environment is going to be operating. If the beauty of the safety case is all of this is in the same place, the operational environment and the airworthiness part of it. So this is where the safety case will have to help us there. This is a problem because the current industry is not using reasoning in those terms. They're usually separate teams.
In the part of the collision, new system, that basically you change the system from this bunch of results to like a pre-calculated data table that you upload and then
ECASX.
And then the system uses. As you said, the system now is much easier to verify because it's a much simpler system. But how can you verify that the actual data that you're producing, the table that you're uploading, is correct? I mean, and that is actually is better than the other system that was in a way more formally.
Okay, so you're mixing two concepts. I didn't say that was easy. That's actually a challenge. The challenge is exactly what you stated. How do you verify that what's in the table is actually what should be in the table? Okay, so it's multiple things. When you the first part is the model is built, and remember that model will be thrown out at execution time. It won't appear, right? It's just used. The model again is produced from historical data, and then it's going to be solved in terms of using some kind of optimization engine for certain criteria. That result of the optimization is what goes into the table. Okay? So you're right, the model is at the core of the verification problem there. The first problem is, do you have the right data? This is the first bad part, because it's all based on historical data. Okay? I haven't seen anything that says we're going to keep rerunning the model to make sure that we have the right model for the current density of traffic, for example. Okay? The second part is, when you do the optimization in the model, you have to discretize that model. That's a model that's actually continuous in nature. It has to be discretized. And the first verification question is, what is the right discretization level for this? Okay? And after that is, did you optimize for the right parameters in your model? So it's a very different way of looking at the problem. And I'm not going to claim we're solving the whole thing. We provided part of the solution, not the whole solution to it. And if you have suggestions, I'll take them. I don't know how much of this might be showing up in. Well, I live in Mountain View, like across the highway, literally from Google. So I see the autonomous car going from my neighborhood. I don't have many details about what's happening, but for what I've been gathering, you guys every time are collecting information about the current ride, right? And it all goes down to a huge database that have like a huge amount of scenarios, and then you analyze those, and that's how you modify whatever the software is doing, right? In some sense, it's a little bit the same problem. It's like you probably have a step where you look at all that data, then you have to model it, and then come up with the software after that does it, okay? I very much doubt that you have a if-then-else type of software going through all the scenarios. So I don't know enough about that part, but it's probably a similar problem that you have to solve there.
I guess to these kind of tools in particular, I'm not sure I followed the safety mode interaction with modeling especially well. But like, does this give you a new perspective on how you would validate that your controls respond appropriately to the dynamics, that you're like crafting safety cases that say, like, in this situation, the controller should do this particular thing or not do this particular other thing?
So that touches a different area that we haven't really addressed. That touches how you come up with your risks given your system. In this case, you're putting it in the system, in a control system framework. There are like a lot of techniques that can be done for this. I mean, the traditional is FMEA type of stuff, but you can be a lot more refined. Truthfully, we haven't addressed this part. We haven't touched that part. We're assuming that there are enough tools to do this out there. The closest we've been doing on this is work that we're doing with Onea in France, where we're looking at the code implementing the controller and trying to prove control types of properties like stability and those kind of things, which is extremely hard to do. Our static analysis is based on abstract interpretation, which means to give you an answer about something, we're building an abstraction around the data points, okay? As opposed to a static analysis where you would go explore every path, what's called the path-sensitive or flow-sensitive analysis, because that doesn't scale, that one. So if you reason about abstraction, then it starts scaling. But when you want, it's too rough. The ones that we have right now is too rough for like stability properties for control theory. So we have to go to techniques that are much heavier. And truthfully, we haven't implemented those in the tools yet. Okay. Thanks.